Hey, what is up, my chemistry people? It is Mr. Boylan, and today, what in the heck are we going to do in this video? We are going to understand acid-base reactions and predict products in acid-base reactions that form water. Okay, now if that content objective sounds a little bit familiar, that's because it was the exact same content objective in the previous video. We're going to break it down a little bit differently here. We're going to talk a little bit more about the application of those neutralization reactions. And as you take a look at your criteria for success, we are going to explain how to carry out an acid-base titration. And then 2, we are going to calculate the concentration of a solution from titration data. In other words, get ready for a really great time. Okay, so first things first, what the heck even is titration? How am I going to apply the idea of neutralization to titrations if I don't even know what a titration is? Well, a titration is just the controlled addition and measurement of the amount of a solution of known concentration, called our titrant, required to react completely or neutralize a measured amount of solution of unknown concentration. So many times we complete titrations to figure out unknown concentrations. Now, the setup for your titration many times looks like what you see on the screen. We'll have a burette for our titrant, we'll have a beaker or a flask for our analyte or our substance of unknown concentration, and then generally we'll have a pH probe connected to some sort of data collection software to help us monitor what's going on with the pH as we carefully measure the amount of titrant that we add. Now, as you look at your screen, you are shown an animation that illustrates sort of what you are going to be monitoring as you perform a titration. You're carefully monitoring how much titrant you add, how much volume of titrant you add, and observing how that affects the pH in an acid-base titration. Okay, now a couple of vocabulary terms before we dive any further into titrations. You need to recognize that the point at which the two solutions used in a titration, your titrant and your analyte, are present in stoichiometrically equivalent amounts is known as the equivalence point. Now, in the neutralization of a strong acid with a strong base, the equivalence point is going to occur at approximately a pH of 7. Okay, so at this point, all you need to recognize then is there are titrations that can be carried out in which the equivalence point does not occur at a pH of 7. We'll learn more about that in AP Chemistry, but just be aware that they exist. So recognize that in a strong acid, strong base titration, you are looking for the equivalence point, or the point at which the pH is 7. At that point, you have completely reacted all of your strong acid with your strong base, completely neutralizing them, and therefore having a pH of 7. Okay, now another really important concept to be aware of in acid-base titrations is the use of an indicator. And an indicator is just something that we add to the titration that will change color at a given pH. Now, ideally, what we want to do is choose a specific indicator that will change color at the same pH as our equivalence point. Therefore, just giving us a visual, letting us know that, oh, we've reached the stoichiometric relationship between these two things. And so as you look at the animation on your screen, notice that the indicator that's being illustrated in this animation goes from a colorless to pink color, indicating that we've reached its end point. And for the titration that you see on your screen, it also changes color at the equivalence point in this titration. Okay, now I've linked to this simulation on the website and I encourage you to check it out. I really like this simulation because it does a really great job of illustrating what's going on in a titration, not only macroscopically, but also sort of at the molecular level. This titration is the titration of a strong base, sodium hydroxide of known concentration. We know its concentration to be 0.200 molar. And we're trying to determine the concentration of a hydrochloric acid solution. It's important to note that we have 60 milliliters of the hydrochloric acid solution to begin with. And as you look at the molecular view, because hydrochloric acid is a strong acid, notice that the hydrogen ions have completely dissociated from the chloride ions in solution. Also notice that our pH starts at a pH of 1, a very acidic pH. Now, what we're going to do is we're going to carefully add specific amounts of our titrant until we reach our equivalence point. I'm going to start by adding 5 milliliters of sodium hydroxide. And notice that as I drop in the base, the hydroxide molecules react with or neutralize the hydrogen ions in solution to form water. I'm going to add 5 more milliliters. Again, notice as I add the sodium hydroxide, the hydroxide ions neutralize the hydrogen ions from the acid molecules in solution. Again, more neutralization. Notice my pH begins to creep up. As I use up those hydrogen ions in solution, it becomes less acidic. 5 more milliliters. I'm so excited just watching these hydroxide ions neutralize the hydrogen ions. Again, 5 more milliliters. I'm using up my hydrogen ions. 5 more milliliters. Oh my goodness, what has happened? At this point, the equivalence point, I have added exactly, precisely, perfectly the volume of my base to completely neutralize all of the acid that was in solution. And because of that, notice my pH occurs at 7. Notice my pH is 7, and notice that the volume required to do that was 30 milliliters of my base. Now, to complete the titration, I'm going to continue adding strong base. Notice this time as I add more sodium hydroxide, there is no more hydrogen ions for it to neutralize. And so my pH jumps way up to the basic range because now I have a bunch of extra hydroxide ions in solution. Again, I'm going to add 5 more milliliters until my titration curve begins to plateau off. Now let's think about what this means. Recognize that the reaction or the neutralization that was occurring between my hydrochloric acid and sodium hydroxide can be summed up here, or using the net ionic equation summed up here. It's important to recognize that the stoichiometric relationship between HCl and NaOH is 1:1. Now the very first thing that I'm going to do is I'm going to determine how many moles of sodium hydroxide I used. I know the concentration of my sodium hydroxide, and I know that I used 30 milliliters of it. I'm going to use my molarity formula, moles per liter. I know my concentration, 0.200 molar, and I used 30 milliliters or 0.030 liters. A quick algebraic calculation here indicates that my number of moles is 0.006 moles of sodium hydroxide used. I need to recognize that the relationship between hydrochloric acid and sodium hydroxide is 1:1. So if I dropped in 0.006 moles of my base, that means it must have reacted with 0.006 moles of my acid. I'm going to once again use my molarity formula here, keeping in mind that I used 0.006 moles of my acid, and that 0.006 moles was dissolved in 60 milliliters or 0.0600 liters. I can very quickly determine my concentration by using a quick division and determine that the concentration of my acid was 0.100 molar. And think about this. I had 60 milliliters of my original hydrochloric acid solution, and I only needed 30 milliliters of the sodium hydroxide to completely neutralize it. Well, because the ratio is 1:1, that indicates that my sodium hydroxide solution, boom, must be twice as concentrated as my acid solution because it only needed half the volume to neutralize it. And we are correct. Okay, so the last bit of your notes there just sort of systematically spell out for you the steps you need to take when determining the molarity of an unknown solution using titrations. First, make sure you start with the balanced equation for the neutralization reaction. And again, this is going to be important because as you think about determining unknowns, you need to know what the relationship is stoichiometrically in the balanced chemical equation. Many times in these neutralization reactions, it's 1:1, but watch out for those strong bases that form from the alkaline earth metals. In that example, the ratio will be 2:1. Step 2 is determine the number of moles of acid or base from your known solution. Sometimes we call it our standardized solution, but use what you know to solve for number of moles. Step 3 then, you're going to determine the moles of solute of the unknown solution using that stoichiometric ratio in the balanced chemical equation. And then lastly, just make sure you determine the molarity or the concentration of the unknown solution using number of moles determined from the previous step and the original volume of the unknown. And that does it for our notes on titration. We'll do lots of examples like this in class. We'll perform a couple of titrations so you get familiar with it.